Hello and welcome to College Algebra 3.3. Today we're going to do polynomial and synthetic division and talk about the remainders and factor theorems. So polynomial division just means to break things down through, well, division, of course. When I'm doing it by a monomial term, I can just do each of them separately. So I can just do 5x cubed over 2x plus 6x squared over 2x minus 2x over 2x, and I can evaluate them all individually. So here, of course, we would eliminate an x. This comes x squared. The 5 and 2 can't be simplified, so I get 5 over 2x squared. Here, I can cross out an x and divide that into 3 over 1, so I'm going to get plus 3x. And here, as a concept, this turns into just minus 1. Unfortunately, sometimes you can't do that because you have some other things going on. So the first thing we can do is long division, where my divisor goes on the outside. And whatever I'm dividing goes on the inside. So I would get 3x cubed plus 5x squared plus 8x plus 7. And I just do what long division would look like normally. So the first thing I do is I look at my first term on the inside and on the outside, and I consider what would I multiply 3x by to give me exactly 3x cubed? Well, that would be x squared. I'm then going to take x squared and distribute it to everything on the outside. X squared times 3x gives me 3x cubed. X squared times 2 gives me 2x squared. Whenever I'm going down in long division, I'm always subtracting. The first two terms should always cancel out. That's kind of the goal here. Then I get 5x squared minus 2x squared gives me 3x squared. I have two terms on the outside, so I'm going to drop down a second term, and I repeat the process. What times 3x gives me 3x squared? That would be x. Distribute my x, 3x squared plus 2x, plus 2x. Subtracting going down, so I flip the signs. I get 6x, drop down to 7, and keep going. 3x times 2 gives me 6x, so I get 6x plus 4 minus minus. I end up with 3. Nothing times 3x gives me 3. Well, I guess 1 over x, nothing nice. So this is my remainder. So when I write my answer, I would get x squared plus x plus 2 plus 3 over 3x plus 2, because I always do my remainder over my divisor, aka whatever I divided by to start. Here, same idea. So whenever I'm missing a term, like for example here, I don't have x cubed or x squared. So I would have to fill in those spots. In fact, I would do it for both equations. So I would get x squared plus 0x plus 3, and I'd get x to the fourth plus 0x cubed plus 0x squared plus 2x minus 3, and I'd repeat the process. You have to fill in zeros for any missing term. Now, as you can imagine, this whole process takes a long time. Well, you have to do it when your divisor is not linear. In this case, this is x squared, so I would have to do it through long division. However, the first one, if I look at it, my divisor, 3x plus 2, was linear, so I could have done a different way. The other way we're talking about, of course, is called synthetic division. Synthetic division, you need to be a linear divisor, and as long as you are adding and multiplying, you're all good. So we would look at whatever we're dividing by. In this case, x minus 3 is linear, so we're going to set that equal to 0. And we're going to solve for x. We get 3. 3 is going in our box. Then I look at my coefficients, and I'm going to list them right here. They are right here, my coefficients. I basically always drop down the first term, or if you want to think about it as adding a 0, which I wrote there. So whenever you are going directly down, you are adding. And whenever you are going sort of angular, you are multiplying. What I mean by that is here, I need to create a new number, so I'm going to do 3 times negative 2, or sorry, 3 times 2 gives me 6. Now I have two numbers on top of each other, so I'm going down, I'm going to add. So negative 3 plus 6 is 3. And then I'm going to repeat the process. 3 times 3 is 9. Add two numbers together, we get 4. 3 times 4 is 12. Add those numbers together, we get 0. The last box is always our remainder box. The second to last box is my constant. The third to last is my x value, and this is my x squared, etc. Always just go up one exponential value. One thing you should note is you should always go down one level functionally. Because at the end of the day, just like on this slide, we're dividing and breaking things down. I broke things down from 3x cubed to just x squared. Same idea here. And because this is always going to be linear, my degree will always go down by 1. So my answer is 2x squared plus 3x plus 4. Let's try another one. Set x plus 3 equal to 0 and solve. We get x equals negative 3, so negative 3 is going in the box. Looking at my coefficients, I can see that I'm missing x cubed, so I'm going to have to fill in a 0 for that. So I'm going to get 1 from x to the 4th, 0 x cubed, negative 10 from x squared, negative 2 and 4. And from there, drop the 1. Negative 3 times 1 is negative 3. 0 plus negative 3 is negative 3. Negative 3 times negative 3 is positive 9. Negative 10 plus 9 is negative 1. Negative 3 times negative 1 is 3. Negative 2 plus 3 is 1. Negative 3 times 1 is negative 3. 4 minus 3 is 1. So this is my remainder, constant, x squared, x cubed. So we get 1x cubed minus 3x squared minus x plus 1 over x plus 3. Just like in long division, it's still my remainder over my divisor. So that part doesn't change because division at the end of the day is still division. Okay. The remainder theorem says that if f of x is divided by x minus k, the remainder is f of k. What this means is your remainder technically would always equal your direct substitution. So if I go back a slide, and if I were to plug in negative 3 into this polynomial, I should end up with exactly 1. So let's try it. We have negative 3 to the power of 4 minus 10 times negative 3 squared minus 2 times negative 3 plus 4. I should end up with exactly 1. Oh, I ended up with all of that in the exponent. I forgot to change it out. My bad. Negative 3 to the power of 4 minus 10 times negative 3 squared minus 2 times negative 3 plus 4. End up with positive 1, so that's all the remainder theorem says. So whatever my remainder theorem is what this should direct substitution, so that's how you can always check. Factor theorem says that if your remainder is 0, it is a factor, which just means it should break it down. So to test, I'm just going to plug this in to synthetic divide. So negative 3 because I had set it equal to 0 and solve. Here we have 1, 7, 12, and I technically don't have a constant, so I'm going to need 0 over there. 7, 12, 0, 1. Negative 3 times 1, negative 3. 7 minus 3 is 4, gives me negative 12, 0, 0, 0. So I would say yes. In fact, if I look at this is my remainder, constant x squared. We see that x squared plus 4x is what I'm left with. If you consider the fact that x plus 3 was just proven to be a factor, I also have x plus 3. And now, looking at this polynomial right here, I can take out an x. So I actually have fully broken down the polynomial. I can tell that x minus 5 is not is a no, but we can always just prove that by checking. So I can do 5, 1, 7, 12, 0. I should get a remainder of not 0 because we just proved that it's not one of the factors. But let's just prove that anyway. Oh, nope. So we would say no because it's not a remainder of 0. So that's what we did on the first day. The second day, we started breaking down and talking about some other concepts that are pretty related. Now, writing an equation of a polynomial, let's say the zeros are these. So these are the answers. Well, then, conceptually speaking, if I took one step back, I would write something like x plus 2 equals 0 in order to get there. Therefore, my parenthetical would be x plus 2. Following that exact same logic, I would get x minus 6 equals 0 and x minus 4 equals 0. So my parenthetical would be x minus 6 and x minus 4. In general, if k is a factor, I know that it's always going to be x minus k as a parenthetical. Here in this case, you could treat this as, x minus negative 2. That's the same thing as x plus 2. So I would get x plus 2, x minus 6, and x minus 4. And then here it says leading coefficient of 1. Whenever it has a problem like that, I'm just going to put my leading coefficient right out there. Four-step process. Find a 0 on the calculator. Do synthetic division to prove it's a 0. What I'm looking for there is an x-intercept. Remember that they're x-intercepts. Synthetic division to prove it's a 0. Well, if it's a 0, by the factor theorem, I know the remainder has to be 0. And also, conceptually speaking, I'm solving for the y value. Well, what's the y value at every x-intercept? Well, that'd be 0. Okay, so here I graphed it, and I'm looking for an x0 that has a nice tick mark. In this case, I'm going to use right here x equals negative 1. So negative 1 is going to go into my synthetic division box. Then I got to look at the polynomial and see if I'm skipping any levels, which I'm not. So 1, negative 3, negative 6, 6, and 8. And just synthetic divide. Boom, I got a 0 for my remainder, so I'm doing pretty well. Now, if I were to assign these, that's a constant x squared, x cubed. I unfortunately don't have a lot of strategies for solving x cubed problems. I could try to factor by grouping, or I could look for another x-intercept, in this case, x equals 4, and synthetically divide again. Only, instead of using the original polynomial, I want to break down the numbers I just got. So that all works out. I end up with a constant of negative 2 and an x squared of 1, so I get x squared minus 2. Now, if you've ever seen the movie Lilo and Stitch, you'll know the core principle is what's called ohana. Ohana means family. Family means no one gets left behind, so do not leave behind these answers. And of course, we're going to turn them into parenthetical, so that x minus k idea. And then last but not least, we're just going to set them all equal to 0. Now, nicely enough, we should know these ones are pretty easy. It's -1 and 4, because those are what we use to synthetically divide. And then, of course, we've got to solve this guy. So I get x squared equals 2, square root. We get x equals plus and minus the square root of 2, giving us 4 total answers. Now, looking at my graph, how many x-intercepts did I have? Well, 1 and 2 we used. We also have a third and a fourth one right there, showing I got them all. In fact, my starting degree was 4. We're not quite to the fundamental theorem of algebra just yet, but the fundamental theorem, which we're going to get to, says that my degree is the number of solutions I should get. So I should get 4 answers at the end of the day, which we did. Okay, next, same idea. Use an x-intercept that works. In this case, looks like you use 2 or -2. For the sake of argument, I'm going to use -2. Just synthetically divide. So this gives me 2x squared minus 9x plus 10. You could factor this, or you could get really, really lazy and synthetically divide with another 0 on there. It's all good. So we get 2x minus 5, and then my zeros I kept with me, so x plus 2, x minus 2. Obviously, this is -2 and 2, as we discussed. And then this one, add 5, divide by 2, divide by 2, we would get 5 halves for that 0. So I got 3 answers, degree of 3, makes sense. Okay, here, I should graph this. So I've already typed it into my calculator, so let's take a look at the graph. And I get this kind of pattern right here. It looks like this intercept's hard to read, so I can't use it, and same with that one. But I get a bounce effect right here at x equals 1. So my graph looks kind of like this. This is x equals 1. Well, we should remember from a previous lesson that if I ever bounce, that implies multiplicity. And in fact, an even multiplicity. I know that I have up to 4 answers, and one of them's right here, one of them's right here. So I know x equals 1 has to have a multiplicity of 2. Which means I can actually synthetically divide with x equals 1 twice. So let's do that. And I can do it again because I have that even multiplicity. Otherwise, I could just plug this in and graph this, and I would actually see that I have x equals 1 as an intercept as well still. So I end up with 6x squared minus 11x minus 10, and I would get x minus 1 quantity squared. And from here, I would try to factor this. So for me, I'd factor by grouping. You could also quadratic formula, -b plus or minus the square root b squared minus 4ac all over 2a. But I'm going to factor by grouping. So multiply my a and c terms. 6 times -10 equals -60. What multiplies -60? Adds to -11. That sounds like -15 and 4 to me. So I get 6x squared plus 4x minus 15x minus 10. What can I take out of those two? 2x giving me 3x plus 2. What would I take out of those two to give me exactly 3x plus 2? That'd be, what, -5? So x plus 2, that's right, 3x plus 2. So we end up with x minus 1 squared, the common parentheses, 3x plus 2, and the outside, 2x minus 5. So we would get 1 with a multiplicity of 2, negative 2/3, and 5/2. Again, that's exactly what my graph indicated with those numbers that weren't very nice, negative 2/3 being right here and about 5/2 being right there. Okay, use this one. Yeah, just talking about earlier. Yeah. Thank you for listening, and I hope you have a great day.